I'm Kohei Hayashi. This is a joint work with Takanori Maehara, Masashi Toyoda, and Ken-ichi Kawarabayashi. Yes, so this talk is about topic detection on Twitter. So first I'd like to briefly summarize about the background. So as you know, as a Twitter is a social network service in which the users are interacted with a short message called tweets. And the uniqueness of the Twitter can be summarized by three properties. One is its huge volume. So there are 41 million users in the worldwide, and also the topics discussed in the Twitter is very diverse. And finally, the speed is very fast. So this means that the Twitter is a promising data resource for topic detection. So topic detection is a technique of the text analysis, which highlights the content of the text as a cluster of words. So it helps users to understand the content without looking over the long sentence. So it's very nice. So the topic detection on Twitter means it is possibly find important news or breaking news and events even faster than the news media. So it's very interesting application. For topic detection for Twitter, we recognize that there were two key challenges. The first one is topic detection in real time. And the second one is how to remove the noise, tremendous noise on Twitter. So I think the first challenge is kind of obvious, so I skip this. And let me briefly explain about the motivation of the second one. Okay, the unique problem in Twitter for topic detection is there are many spam messages which are generated by not human. Okay, so a typical example is a tweet button, which is embedded in a news article of the website news. So by clicking this button, as you know, this duplicates the same messages, and it automatically posts in the timeline of the Twitter, which means it exaggerates the word co-occurrences. And because topic detection is extracting the word cluster by looking at the co-occurrences, this is a very problem because this exaggeration hijacks some other important topics. So we need to remove them. Yep. So to tackling these challenges, we propose a new streaming algorithm for topic detection based on the non-negative metric factorization, for shortly NMF. So there are two important characters. The one is it's very highly scalable. Actually, so it is possible to handle with 20 million by 1 million sparse matrices, sparse metrics for each second. And also, it is automatically detect topic hijacking and removing such kind of spam topics. Yeah. Also, I'd like to highlight the technical viewpoints of these two characteristics. To achieve the first contribution, we reformulate NMF in a stochastic manner, which means we can use a stochastic descent method, which is the first. And actually, so it is possible to process the data by a linear time with non-zero element of the input matrix. For the second contribution, we use the technique of statistical testing, So it is possible. It enables us to detect such kind of topic hijacking by in an objective way. Okay. So first, I'd like to talk about the streaming algorithm. And before that, I'm sorry, but let me briefly introduce about the topic detection by NMF. So the NMF tried to find a word cluster. So basically, it means that from the tweets, we can generate this network, which is connected by. So if a user tweets some messages, and which that tweet contains some word, the user and word has a edge. And by collecting such kind of relationships, we can construct this network. And basically, so the topic detection is finding these clusters which are tightly connected. Now we consider a frequency table by accounting this from Twitter timeline. And actually, so finding such kind of cluster is corresponding to decompose this frequency table to as the sum of the rank 1 non-negative matrix. And this decomposition is called NMF, actually. The problem of NMF is formulated by this optimization problem. So basically, this objective function consists from the squared loss function and the regularization term. Also, this problem is non-convex. We can solve this problem by using a simple alternating gradient descent method with projection. So iterating these steps, which is updating U with fixing V and updating V with fixing U, leads to convergence to some local minima. And yeah, so NMF, that algorithm works very well for a static matrix. But in our case, in Twitter, so the matrix is changing for over time. So actually, so for each time t, we observe a new matrix xt. So we need to keep tracks of that matrix. So now specifically, we consider to keep track of the averaged matrix, which we denoted by expert t. So as a naive approach, we can solve this. We can decompose this average matrix by a batch NMF algorithm. But as you know, it's very time-consuming and it's not so efficient. So it should be more efficient way. Yeah. And we find that. So actually, the key idea here is decomposing this loss function for each time depending terms. So because this expert t, it can be written as a sum of the xt. So so this function is a square norm. So the sum of the inside of this square norm can be moved outside of this square norm. And moreover, if this xt is can be seen as IID random variable, then this sum operator can be seen as an expectation operator. So we can use the same technique. So we can move this expectation to the outside of the squared norm. Actually, so this is very nice because now the loss function is written as an expectation form. So we can use stochastic optimization techniques. And yeah, actually we use the SGD. by using SGD, we can develop a streaming algorithm. So the main differences from the batch algorithm is, so there are 2 points. So the first, we introduce a matrix, AU and AB, which slightly improves the convergence speed. And also we replace the full gradient to this, the gradient which only using the current sample XT. And yeah, and because this is the stochastic gradient descent, the convergence property is maintained. So it is guaranteed converging to some local minima of the loss function over the averaged matrix, if under the condition that the X is randomly IID. Yeah. So let me summarize the advantages of our algorithm compared to the batch NMF. So first, it is very fast. So now in our algorithm, we only need to update U and V once, just once, for each time T. And also, the update cost only depends on the number of non-zeros of XT, which is drastically smaller than the non-zero element of the averaged matrix. And also, it is memory efficient because this update only requires the current observation. So we don't need any past observation. So we just discard them. And finally, it is kind of interesting point, but this update rule has a natural smoothing effect. So by rewriting the update rule, we can find that this new solution can be seen as a eta t weighted average of the previous solution and the one-step NMF solution of the current observation. Because this current one-step NMF solution is problematic because XT is very sparse, so the sparsity problem occurs. But by using this averaging, eta t averaging, the sparsity is mitigated by so the previous solution interpolate the sparse area of the current solution. Yeah, and yeah. So now we would like to talk about the second contribution. So let me remind us that the problem here is so there are some spam topic, so we need to eliminate them. So the goal here is to find hijacking topics, spamming topics. So the idea here is checking the distribution of all topics. This idea is come from our hypothesis. That is, the word distribution of a hijack topic should be different from the word distribution of a normal topic. Yeah, because the hijack topic is generated by a non-human, so there should be some difference. But to checking this distribution, we need information about the topic-sensitive distribution of word. But fortunately, this is possible to obtain because so actually NMF estimates the topic-specific word distribution as its parameter. So let me explain this. So Xij, this is a frequency matrix. So this can be seen as a normalized probability, a joint probability of the user I and word j. And this, by using the base rule, we can rewrite this as a summation of the user distribution given topic and as a product of the user distribution given topic and the word distribution given topic. This is exactly the same that the NMF does. So yeah, we can estimate this word distribution by V. Okay, yeah, so I would like to define what is normal topics. So in our intuition, in a normal topic, so many users are involved because it's the many users interested in the topic, so the many users are involving to the topic. So which means that the word distribution is mixed by many different vocabularies because every user has a different vocabularies. So which means that the word distribution follows a heavy-tailed distribution. So motivated by this intuition, we define a normal topic as follows. So we say topic R is normal if this word distribution is following the power distribution. The power distribution can be written as like a line in a log-log plot, and alpha determines a gradient. And also for hijack topics, because the hijack topics are generated by non-human, and it's repeatedly using the same text, which means that the distribution follows like uniform having a uniform probability, and the tail is nothing. This leads this definition. So topic R is hijacked if this distribution, a word distribution following the step distribution. And this rank means a position, it's the length of the duplicated text. Okay, and so now we define the what is normal topic and what is hijack topic. So now we can find the topic hijacking by using a statistical test. So indeed, by computing this log likelihood ratio, this theorem holds. So this looks like a bit difficult, but the important thing is if we have a sufficiently large number of data, this log likelihood ratio is following to the Gaussian distribution, which has a variance 0 mean, and the variance is sigma squared, and that sigma squared is computed, can be estimated by this following this formula, and it is can be computed efficiently. So combining this idea, we can automatically detect the topic hijacking by checking for each topic and estimating the distribution parameters and checking its p-value. Yes. And finally, we like to explain about the experimental results. So for data, we use a Japanese Twitter stream, which recorded in April 15 to 16 in 2013. So it's a 2 days long data. And we separated this stream as for each xt having 10,000 non-zero elements. So first we compare the runtime. So because some algorithm doesn't work in a whole by using the full stream, so we divided the data as a 1%, 10%, and the same as the total data. And we easily find that our method is the fastest. So actually, it's 5 to 20, 150 times faster than other method. Yeah. And actually, the filtering cost is almost ignorable. Also, for the quality of evaluating the quality of the topic, we measure the perplexity, which measuring the similarity between obtained topic distribution and the target distribution. So lower is better. And the result also shows that in 10% and 100% data, the streaming NMF achieved the best performance. Also, this filtering it's kind of not looks not big, but it's sufficiently improves the perplexity, the performance. Okay, so this is a summary of this talk. So we propose a streaming algorithm for Twitter topic detection, and we find that this works in real time, and also filtering spam topics automatically. Thank you very much.
Fantastic. So we have time for some questions. Go ahead.
Interesting talk. Usually, when you move to stochastic methods, you increase variance of solution significantly. Did you experience that? And did you do anything about potential increase of solution variance?
Currently, we don't have a good idea to decreasing such solution variance, but yeah, I have no idea.
Did you consider using covariates, something like that?
Covariance of what?
Covariates.
Covariance of what? Sorry, I don't understand.
Okay, let's take it before. I have another question. It's okay?
Yes, go ahead.
Okay. So the idea of filtering hijacked tweets is based on the assumption of using zip flow distribution of words.
Mm-hmm.
Well, I think when hijackers learn about this technique,
mm-hmm.
they can easily add it,
Sure.
and even making the situation worse because it would skew the distributions in such a way that even normal topics would look very suspicious.
Mm-hmm.
So did you think about this?
It's a very good question. So some people know this fact and doing some technique to skewing this distribution, then this method doesn't work. So yeah, currently we don't have any good idea. Yeah.
Okay, let's thank our speaker.